Hello everyone, I'm Rúben, a master's student in biomedical engineering and part of the biomedical imaging laboratory of Inestec. This work appears in a new project in partnership with the Hospital Center of Gaia, Portugal. The main topic is segmentation of cardiac tissue in CT image for diagnosis of coronary artery disease with the guidance of Professor João Pedrosa and Francesco Renna. Basically, this work is still preliminary and focus is on segmentation of the pericardium in CT image, and I will present a little of my work. Here is a brief slide about the content that I will discuss, that is the disease itself, the actual ways of diagnosis, and how our segmentation of the pericardium may help in a future diagnosis, as well as improvements and future work. Turning now to the disease, so CAD, or coronary artery disease, is the most common among the cardiovascular disease, which is the leading cause of deaths in the world, causing about 17.9 million deaths per year, and where currently about more than 75% occur in low and middle income countries. Many risk factors increase the probability of CAD, including cholesterol, diabetes, smoking, obesity, or genetics. But how CAD happens? So CAD happens when the coronary arteries become hardened and narrowed, causing the reduction of blood flow to the heart muscle, leading to ischemia. This is due to the buildup of deposits of calcium, fatty lipids, or inflammatory cells, called plaque, on the inner walls of the coronary arteries, also named as atherosclerosis. As a result, the heart muscle can't get the blood or oxygen it needs, so this can lead to chest pain, angina, or a myocardial infarction, so an heart attack. So nowadays, quantifium calcium deposit in the coronary arteries through calcium scans is the most common technique for screening CAD. A coronary calcium scan uses computer tomography CT to detect calcium deposited in the coronary of the arteries of the heart. So a higher coronary calcium score suggests a higher chance of the presence of a plaque, as we saw before, and a higher risk of a future heart attack. However, CAD, especially in people below 50 years old, can be present without calcium and may not be detected by this technique, which leads some patients to be misdiagnosed. In order to overcome this, new studies for new ways of diagnosis have emerged, and it has been suggested that the volume and thickness of the epicardium adipose tissue will be involved in CAD. So the epicardial adipose tissue is situated between the heart and the pericardium, as you can see from the image. So its proximity to the coronary arteries suggests that an alteration in this tissue could also play an important role in CAD. So it is important to be able to segment this structure. The pericardium is a sac that surrounds the heart, as you can see from the image on the left, as well as the CT image on the right, representing the outline around the heart. So with protective and lubricating functions. The segmentation of pericardium is extremely important because it allows not only a later quantification of the epicardial adipose tissue, but also segmentation of other cardiac structures such as atria, ventricles, or blood vessels, relevant for diagnosis and prevention of various types of heart disease. So, the objectives of our work are to train a model with a UNet architecture using a public dataset, and then testing the generalization performance of the segmentation model with a private external dataset from Hospital Center of Gaia. The approach followed for segmentation is presented which consisted of two primary parts, so image registration and then segmentation of the pericardium using deep learning. But first, I will present the data sets used. So the first is a private external data set collected in Hospital Center of Gaia that will be used to test our automatic segmentation model. This data set includes 20 CT scans from 20 patients with a total of 909 slices. All slices were manually segmented by Carolina Santos, a medicine student at University of Porto, where the red pixels represent the pericardium, as you can see. The other dataset will be used to train the model is a public dataset available online from Rio de Janeiro, containing 20 CT scans of the heart belonging to 20 patients, with a total of 878 slices in DICOM format with a size of 512 pixels. In this case, a group of doctors and specialists manually segmented the epicardial tissue in red and the mediastinal fat in green, as you can see also from the image. It should be noted that this segmentation was done after converting the DICOM image into a specific range to highlight the fat, and we don't already have the pericardium labels. It should also be noted that the DICOM images have different proportions and alignments than the images containing the labels, so the ones manually segmented by experts, that we'll need to fix for the automatic segmentation of the pericardium. In this way, we went on to a process called image registration, which consists in matching the same characteristics between the two images to find alignments in order to align the labels to the DICOM image. To facilitate this whole process, we start by converting the DICOM image in the same range as the image where the labels are contained, as you can see from the pictures. One particularity in this conversion is that every pixel that is not within the given range is painted black on both occasions. Basically, there are two main definitions to keep in mind. So, key points and descriptors. The key points are simply points that stand out on the image representing specific patterns or particular features, which are unique and can be easily tracked and can be easily compared. Descriptors, as the name implies, describe the features found to compare them with other images and find the same characteristics, being able to align them. For this purpose, we use a method called orb to detect and describe the key points. The orb works as follows. So first, it uses an algorithm named FAST to find the key points, which are represented in blue in this example for a patient slice. And FAST assumes one parameter, the intensity threshold between central pixel and surrounding pixels in a circular ring above the center. Then it uses brief, which is a binary descriptor that will describe each of the key points as a set of binary features relative to a condition that compares intensities of pairs of pixels around the key points. Then use the brute force to compare and match the key points between the two images, as you can see. So brute force takes the descriptor of a key point in the first set and match it with all other features in the second set using some distance calculation, in this case Hamming distance, and the nearest one is returned. And finally, the ransack algorithm to find the transformation matrix to apply in the image that we want to register, and as you can see, the two images are already aligned as intended. It should be noted that images are misaligned in exactly the same way within each patient, so therefore only one manually chosen transformation matrix is applied per patient. So in total, we'll have 20 transformation matrices, and we apply these transformation matrices to the masks, and the results are visible in the example, where on the left no image registration is used, and we can see that the mask is completely out of alignment with the DICOM image, and that on the right, when the image registration is performed, so the mask is aligned. With this correction made in the masks, we can now move on to the elaboration of the model for segmentation of the pericardium. Still, we do not have the pericardium data set, but as the epicardial tissue is delimited by the pericardium, we use the convex hull method to delineate the contours. So the convex hull is the smallest convex shape that contain all the pixels, which can be found with a set of iterations in which is constantly evaluated whether or not a point is within a defined facet, and to initialize the algorithm, 2 points are selected in two-dimensional cases. If possible, points with either a maximum or a minimum coordinate. Then the farthest point of the line formed by these 2 points is selected in order to form a triangle, and all points that are within this triangle cannot be part of the convex hull, and this process is repeated to triangle lines and so on until no point is left and the convex hull is bounded. The result is presented in the image below. Now that the labels are set, we use the UNet architecture for the model, which usually has good results for segmentation of biomedical images. It has a U-shape and consists of 2 essential parts: a contracting part that with successive convolution will increase the number of features of the input image, and then an expansive part that will make successive transposed convolutions followed by concatenations in order to increase the image back to this initial size. So to train the model, the data was divided as follows. So 60% of the patients were used for training, 20% for validation, and the remaining 20% for testing. 2 different input sizes were tested to evaluate the importance of contextual information and network receptive field. So a model with 512, the original image size, and another with 256 pixels. The binary cross entropy function was used for the loss and the Adam optimizer. To evaluate the performance, the dice was used that evaluates the degree of overlap of 2 images through their pixels. The value of dice ranges from 0, indicating no spatial overlap between the 2 segmentations, to 1, indicating complete overlap, and of course we want as close to 1 as possible. So for the results for the public dataset, as you can see from the table, we obtain slightly better results for the model trainer for 256 pixels image with a dice of about 87% versus 83%. As you can see from the image, the 256 model looks like slightly more similar to the pericardial labels. However, for the last slice of the patients in which the pericardium is not very visible, and due to the presence of other organs in CT slice, the 2 models do not present good results. And so for the private Gaia data, as expected, we obtain slightly worse results with a decrease around 6%, but also with better results for the 256. So this is maybe because larger image size results in decrease in the size of the receptive field, thus giving less contextual information to the network, which can be important for segmentation. We highlight the example of the last row of the figure, that it seems that the patient has a very calcified aortic valve, and we can see that the model failed to segment this pericardium around it. So around this valve. This example shows the need to train the model for more patients with greater variability in order to make the model more generalizable. As a conclusion, this work is still preliminary, and it is intended to segment other structures of the heart to help diagnose of disease, namely pericardial post tissue. However, these results indicate that reasonable performance can be obtained with a small number of patients and only a small decrease in performance in an external dataset. The future work to improve performance and robustness must focus on increasing the quantity and variability of training and testing data, and integrating contextual information to increase performance in the lower pericardium. So thank you all. Do you have any questions?